All right, we finished up electrostatics and electrodynamics or electric current, and that's going to lead us into the other half of this as far as particles and how they interact. So we're going to look at magnetism. Um, there's a really interesting history behind magnetism and how knowing that this is a phenomenon came about. But the term magnetism actually comes from Magnesia, which is a coastal district of ancient Thessaly in Greece. And are in this area, they had these stones that they were able to find on the ground. They were called lodestones. And they had this really weird property where they would actually attract pieces of iron. So said here's a picture of Thessaly. Apparently it was called City of Races. So you can see they've got their what's left of their track here. Over on the right, we've got two pictures of lodestones. The N and the S stands for like the north and the south pole of a magnet, so you can see where these poles are. And then just a lodestone can actually attract iron filings and iron objects like these nails. A legend has it, I don't know if this is true or not, but soldiers would notice, or at least people in general would notice as they walked over these lodestones, the nails holding their shoes together, they would actually sort of stick. And they really weren't sure why, but they knew that these lodestones had this weird property. Uh, it wasn't too long before magnets were fashioned into compasses. Magnets just being these pieces of lodestone and like iron shavings that were magnetized. You could actually magnetize iron shavings by rubbing them against lodestone. So, um, and the Chinese were using this for navigation purposes in like the 1100s. Even before that, there's evidence that essentially compasses were used for divination. Uh, and this image up here is actually a type of compass, but it wasn't used as a compass. It was essentially used as like fortune telling. Um, and this is from like 200 BC. So the whole idea of magnetism has been around, or at least knowing that something could be magnetized has been around for a long time. Just knowing how that happens remained a mystery for a long time. Um, so this guy here, William Gilbert, I'm not sure if his name is French or not, so I might be mispronouncing it. Um, he made magnets by rubbing iron against lodestones. And when he was doing this, he actually realized, they always align north to south. So maybe it's some sort of magnetic properties of the Earth. So he was the first to sort of propose the idea that, oh, maybe the Earth actually has some sort of bulk magnetic property. In 1750, John Mitchell uh, found that magnetic forces decrease with distance. Um, yes, I can't read my own text. So magnetic forces decrease with distance from magnetic sources. So this is starting to look like our whole, if you remember Coulomb's law, F equals K Q1 Q2 over R squared, where the force decreases with distance, right? 1 over R squared. So we're sort of looking at the same rule except for magnets. So this has given us our first hint that maybe magnetism and electrostatics and electric forces are somehow related since they're acting similarly. These two ideas actually sort of developed side by side until about 1820. That's when Hans Christian Ørsted actually discovered that an electric current actually will affect a magnetic compass. So he was actually doing a demonstration about electric current in his class. And as he was like turning the circuit on and off, that's when he noticed every time he turned it on, it would deflect a compass also on his desk. When he turned it off, the compass would go back to pointing north. So through an accidental demonstration for his students, he actually concluded that magnetism and electricity are actually somehow related. So hopefully this GIF is playing for you. But essentially, every time a current is pumped through this circuit, the compass, the red and blue bar there, will actually rotate because the current is, for now, we don't know how yet, but we'll talk about it later. The current is somehow inducing its own magnetic field. Um, Someone we've already talked about, Andre Ampere, he proposed finally, he put all this together and said, well, maybe electric currents are actually the source of all magnetic phenomena. So now we're finally getting to putting two and two together, so to speak. So if we have electric currents, we get magnetic phenomena. So maybe anytime we see magnetism, that has to do with some sort of moving charge. So we can sum this up and just say magnetism, we think, but we're getting there. Magnetism is equal to a moving charge. Uh, Recall that the force between electrically charged particles can be determined by using Coulomb's law. Okay, I've already written that out. Just that F equals K Q1 Q2 over R squared. When we use Coulomb's law, this works for stationary charges, right? So they're static, they're not moving. It's just you have two charges, maybe one's positive and one's negative, and they're just chilling. They're interacting, but they're not moving. Um, that's because when particles that are charged start moving, uh, things get way more complicated. So if they're moving, in addition to the electric force, so in addition to K Q1 Q2 over R squared, there is another force that's added for moving charged particles, and that is the magnetic force. Um, so if you have static charges, you just have E, electric field. Oh, that should say moving, but I can't write. Let me see. Great, now I can erase it. Right. So this says moving, even though it doesn't look like it. So in the situation where you have moving charges, you have electric fields and magnetic fields. So the whole idea here is that electric and magnetic forces are two aspects of electromagnetism. So electromagnetism is a big thing, but it shows up as an electric field and a magnetic field. It's just depending on your experiments, you don't always see both of them together. You're just seeing a piece of this broader idea of electromagnetism. All right. Let's talk about the components of magnets. Since we know where they came from, we know how they were discovered, we know for some reason magnets are related to electric current. Even though if you hold your kitchen magnet up to your refrigerator, you don't have it hooked up to a circuit, but yet somehow it's still related to current. So let's talk about how that works. Um, so again, the forces that magnets exert on one another are similar to electrical forces because both can attract and repel without touching. So the key here is the attract and repel over a distance, right? So we have some sort of distance r where they're separated. Now the strength of the interaction depends on that separation distance. Okay. So the strength depends on separation distance. So again, we have this 1 over r squared inverse squared law. So electric charge, whether positive or negative, is responsible for electric forces, but magnetic poles give rise to magnetic forces. So as far as electronics go, or yeah, electronic forces, you've got your protons, you've got your electrons. Those are essentially the sources of your electric field, whereas the electron will be going in. So those are your carriers of your electric field. When it comes to magnetic fields, you have your poles. You have your North Pole and South Pole. There's one more point I want to make. Yeah. It might be on the next slide, but I'll go ahead and say it here. Unlike electric charge, so you can have just a proton chilling by itself. You can have an electron by itself. It can be isolated. You cannot isolate a magnet. Magnets always have to have at least a north and a south pole. You could have multiple of those. You'll remember the lodestone from one of the intro slides where it had several different poles, but you have to have a north and a south. So these are must-haves. You can't have just a north pole by itself or a south pole by itself. In the simple bar magnet, and this is true for most everyday items, you can get some weird stuff that has really weird locations, but in simple bar magnets, you'll have a single north pole and a single south pole, and they're located at opposite ends of the magnet. A north and a south. You can also bend these magnets, and you can make like a horseshoe magnet. And it keeps its poles at each end, as you can see here in the picture. You still have your north and your south pole as that's bent. As you probably know from experience, the like poles repel each other. So north repels north and opposite repels opposite, but opposite poles attract. So north repels north, south pole repels south pole, but opposite poles will attract each other. And this is just like electric charges. Electrons repel each other, protons repel each other, but those two, proton electron, are attracted to one another. Here's the point from last slide. Just reiterating that charged particles can be positive, negative, and isolated, but magnets are always found having a north pole and a south pole. Or if you find a south pole, you can always find a north pole somewhere on the object. What's really interesting is breaking a bar magnet in half doesn't isolate the poles. It just makes two magnets. So if we were to take this horseshoe magnet and break it in half, we wouldn't have separated poles north and south. What would happen is we would just get two new magnets. So we'd have this magnet and this magnet. So they're all north and south poles. We could even break it again, and we could have four magnets. all with their own separate poles. So every time you break a magnet, you just get a new smaller magnet. Um, so there's no way to just simply break a magnet and have an isolated pole. So I've mentioned it before casually so far, but the space around the magnet, just like a charged particle, has a field. And this is a magnetic field. And it can just sit right on top of an electric field or any other field. All these fields, you can just smush them together in space. Um, you can actually see the shape of this field if you essentially just dump some iron filings onto a magnet. So something we would do in undergrad is we would put a clear like piece of glass over a magnet, and then we would dump the iron filings out, and then the iron filings on top of the glass would start forming the field lines. You can see that up here. So that's exactly what's going on here. This is essentially just iron filings poured out on a thin piece of like glass or plastic with a magnet underneath. So the field lines spread out from one pole and converge on the other. So we have direction now. Okay, now I can erase. That's so strange. Okay, so we have a direction now. And where these lines are closer together, the field is stronger. So that means up here in this figure, we have field lines coming from the North Pole, and you can see them here. They're going to the south. There's another one. I'm not going to try and draw all of these, but you can at least see them in the iron filings. We'll do this one too. And you can see here they're close together, which means this is a strong magnetic field. But then over here, let's see, let's find a good spot. Over in this area, they're less defined. The filings are a little further apart. So there you have a weak magnetic field. So the direction of the field lines outside a magnet is from North Pole to South Pole. So there's our directionality. I can reiterate that here. So just like charged lines or electric field lines, same idea. We have a direction. We've been talking about it, but magnetism is very much related to electricity. When at rest, a charge is surrounded by an electric field, but when it's motion, it has both. Okay. What's really interesting and wild and will really hurt your head is the magnetic field is due to distortions in the electric field caused by motion. Okay. So essentially, what that means is as a particle moves through space, you're going to get distortions in the electric field, and then that is going to sort of start up the magnetic field. And it's weird. Albert Einstein proposed this in his special theory of relativity in 1905, but he was able to actually put the math together to show that the electric field and magnetic field are related. And what's really creepy, we won't go into it in too much detail here, but magnetic field is relativistic. So the reason that's creepy is because that means it depends on how you watch a charged particle move, whether you see the magnetic field or not. If I'm sitting here at my desk and a particle comes by, I can see the magnetic field. If I run along beside the particle at the same speed the particle's moving, I cannot see the magnetic field. So I think it's really creepy that the magnetic field will show itself depending on how you look at the thing that's moving. It's really weird. Your book goes into a little more detail if you want to read about it. It's in one of the first four sections. So electrons are charged particles. Okay, yes. So now the question is, if we just have a regular old magnet sitting here, if I hold up a bar magnet, let's say my marker is a bar magnet, I have a north and a south pole, but I don't have an electric current running through it. But an electric current is supposed to create a magnetic field. So if I have a magnetic field, where's my current? Where's my moving charge? So it turns out the electrons in the atoms of my magnet are actually causing, they're responsible for that motion to cause a magnetic field. So the electrons in the atoms, they're always moving around the nuclei of atoms, right? So we have electron revolution. So we have electrons zipping around the nuclei of atoms. And we also have electron spin. So you think about spin, and this is not quite right, but it's close enough. So you can think about spin as like you've got the sun and the earth revolving around the sun, but then the earth also spins on its axis. We can think about electrons doing the same thing. So you've got your nucleus, you have your electron. So you have the electron zipping around the nucleus, but then you also have the electron spinning around its own axis. So those are two different ways that charges are moving within a magnet. And you can see here, you've got some rotation on the electron, and that's sort of generating this magnetic field, these magnetic field lines. So essentially every spinning electron is a tiny magnet. You could get a pair of electrons spinning in the same direction, and that makes a stronger magnet because they're both sort of adding up. You can get a pair of electrons spinning in opposite directions, and they will actually cancel each other out. So this is actually why most substances are not magnets. In most substances, magnetic fields cancel. But this is not the case for a few select items like iron, nickel, cobalt, that kind of thing. But generally, there's enough atoms doing their own, there's enough electrons in an object doing their own thing to where they just sort of cancel each other out. So you don't get that net magnetic field. I do want to point out that you can actually mess with magnetic fields. So if you have two opposite or two magnets that are laid opposite to each other, so you have a north here and a south here, you'll see that you can start making these field lines that reach out and connect to other magnets. They don't have to always go back to themselves. While this is reaching out, you also have some of these field lines that go to the same magnet. Same thing over here with the south to north. But if you flip these magnets, you can see here we now have a north-north. You can see that they don't interact with each other. If you look carefully, you can see these start to turn away because they are really not wanting to touch each other. But they will go back on themselves. So we have these aligned atoms. Well, we have an atom that can be aligned because of its electrons zipping around and the electrons spin. If everything works out with that atom, where the electron will start providing a magnetic field, it could sort of propagate to other atoms. So then you get clusters of atoms that align, and this is called a magnetic domain. So that's just a chunk of a material where everything's lined up to actually start causing the additive effects and make a larger magnet. And of course, these domains are made up of billions of aligned atoms. The domains themselves can also be aligned with each other. So we can go from single atoms to domains and then aligned domains with each other. So you can see this happen when you take a magnet and touch it to like an iron nail. The nail itself is not magnetic, but after you put it on a magnet, the nail then can become magnetic. So if you take a natural piece of iron, you can start aligning these domains when you bring it near a bigger, stronger magnet. Of course, if you take that piece of iron away, the domains will return back to their random states. But if you apply a really strong magnet, you can actually create all those domains, have them snap together, and then that object will actually stay a permanent magnet. Of course, if you were to drop or heat a permanent magnet, it will decrease its strength because when you drop it or heat it up, you start letting those domains become unaligned again. So you can see that here. Normally with an iron filing or something, you would have all these domains just pointing in crazy directions. It's all random. If you sort of bring a weak magnet over, you can start seeing some alignment. So every now and then you'll see some of these start to try and line up in the same direction. You can see that we have a small s and a small n, so we're starting to get some magnetism out of this. Now, if we have a strongly magnetized piece of iron, we have a strong south and north pole, and all these domains are really well aligned. In this case, if we do have a strong magnet, we could break it in half, and then we just get two of the same magnet. So all these domains are still aligned. We get a new north and south pole. And if the magnetization is strong enough, it'll stay like that until you either heat it up or drop it. We can just look at one example real quick from the book. There's no math in this chapter. The next chapter gets a little mathy. But the first question here is essentially just why can a wooden pencil become magnetized? And it's simply because wood has no magnetic domains. Permanent magnets have to have those magnetic domains for them to be magnetized. All right, so with that, I'm going to stop. Again, this first week is just prepping us for the next module. So the next module is going to be a little more intense. It's magnetic induction. It's going to be more mathy. This is just to cover the concepts. So this lecture here was just to describe where magnets come from and their parts, their poles, their domains, that kind of thing. So if you have any questions, please let me know.